Hi, my name is Mark. I'm one of the maths lecturers at New College Durham. Today I want to talk to you a little bit about A-level further maths, give you a bit of insight of what it is, why it's such a brilliant qualification, but also just get you thinking about maths in a slightly different way as well. So before I start, just to clear up a bit of information about further maths, it is an entirely separate A-level to maths. If you want to study further maths, you will also study maths as well, but you get two completely separate A-level grades. Further maths is brilliant if you're looking at going into abstract and technical engineering, but if you're also looking at sort of maths and physics degrees and futures in those sorts of areas, it is an outstanding qualification to have. At the end of the video, there is a little short overview of what students who have previously studied this subject have went on to do at university. It is actually much more varied than you would probably think. Now, if you're trying to think if further maths is the qualification for you, my email address will be at the end of this video so you can contact me with any questions that you may have. Our entry criteria are the same as maths, however, we look for a 7 in GCSE maths instead of a 6. In thinking about the qualification, the starting point for further maths and maths is pretty much similar. However, you just need to be a bit more confident with algebra, competent in how you approach questions, and a bit more fast and fluid in the work that you can do. So there's not really any topics that I would say, oh, you need to know this topic to be really, really good at further maths in comparison to maths. It's pretty much the same starting point. You just need to be a bit more confident and competent to be able to access the further maths materials and the speed at which it goes. So with that out the way, let's focus on the good stuff. Let's focus on the interesting stuff. Let's actually look at the maths. And what we're going to do is take a very basic concept and think about what is a number. So, what is a number? Well, a number is essentially just an object that we use to quantify or count or label something. Basically, it's like asking what is a word. A word is essentially a noise we created because we think something is important enough to have a noise in order to explain it or describe it, and then collectively got everyone to agree that, yeah, that's the noise that means that thing. It is the same with 5. The numeral for 5, the word 5, what 5 represents, requires an entire civilization of people to come together and decide that is what it is. So extending on that, it's how do we actually think about numbers and how do we write numbers and what type of numbers do we have? Well, basically, number systems start with what we refer to as natural numbers. Now, natural numbers are often typeset with the letter N, like so. Now, natural numbers are numbers that you tend to see in nature. They are whole numbers that are positive. Things like 1, 2, 3, 6, 800,000. They're things that you can point out and quantify. And these would have been the first types of numbers that people would need to deal with and give essentially symbols and sounds to. How many cabbages do I have? 4. How many children do I have? 2. How many people are coming over that hill with spears? 6. Those types of things are very, very simple and easy to quantify. After that came integers. Now, integers are represented by the typeset Z. And integers are all natural numbers as well as your negative numbers. So all possible values there, etc, etc, etc. They include all the natural numbers, which actually are sometimes referred to as Z plus, because they are essentially positive integers. Now these, if you think about the dramatic scenario, how many people are coming over the hill with spears? The answer is 6. I've got 4 cabbages. They take 3 cabbages away from me. So there comes the concept of negativity. Things being taken away, the idea of debt in society and things like that. We have this conceptual need for a negative as well as a positive. So that leaves me with 1 cabbage. So what I decide to do in all of this is I half my cabbage. I cut my cabbage in 2 and I go, brilliant, now I have 2 cabbages. But I get the concept of size as a human and I go, no, I don't have 2 cabbages. Cutting something in half does not suddenly give me 2. I haven't gained anything more. I have the same amount of cabbage. So this is where the concept of fractions comes in. And you can see how this type of thing again would naturally occur. It would start to appear in the world. And these are rational numbers next. So rational numbers are represented by the letter Q. And rational numbers are any fraction. So we've got a half, we've got 7/6, we've got -9/4. All of those and everything that went before it. Because the number -1 could be written as -4/4. The number 4 could be written as 16/4. There are lots of different ways that we could represent those, so they are still all rational numbers. And then civilization, you could see, get more sophisticated. And you would have to start thinking about things that aren't so easy to work with. Now, surprisingly, a lot of these numbers that come next have been around a lot longer than you would think. So ancient Mesopotamia, there are clay tablets with examples of sort of trigonometric ratios and things on there. It's so I would say ingrained into culture and society in general, this sort of level of mathematics. This isn't new stuff. So next is real numbers. And real numbers are represented by the letter R. And real numbers are the things that cannot be written as fractions. Things like √2, things like pi, and Euler's constant E. Now, these are referred to as irrational numbers. However, real numbers are that set of irrational numbers and all other numbers that go before it. So why is all of this important? Well, this was just a way of illustrating that kind of the number system that we have is reactive. Yes, going back to the number 5. Number 5 means something because collectively we have allowed number 5 to mean something. But 5 doesn't exist naturally. It is something that has been created by humankind in order to explain something. So all numbers are essentially reactive. They only exist because we have a use for it. So basically, none of this is really set in stone. It's not existed since before humankind. It means that if we have a use for something else, we can make something else. It doesn't have to just be this. And in fact, it isn't just this. So why is there more to the number system in comparison to that? The key thing for that is the concept of vectors. Now, you do a little bit of vectors in GCSE maths, but you should also be aware of it from physics. And it's more the physics definition at this moment in time that we want to focus on more. A vector is essentially a quantity that has both magnitude and it has direction. Now, magnitude basically just means size. So it simply has some form of size and it has a direction in which it is going. Now, numbers we tend to associate with quantities and measurements, and we tend to look at measurements as being vector quantities or scalar quantities. So things like velocity we tend to say is a vector, and speed is the scalar version of that. We say things like acceleration is vector, force is vector. But what about numbers themselves? Not just the units that they represent, but physical numbers. Numbers are themselves vector. You go, how can a number be a vector? Well, if you think about a nice basic number line, when you were in primary school, above the board, in your classroom, there was highly likely a nice basic number line. 0, 1, 2, 3, 4, 5, all the way up maybe to 9, to 10, to 12 and things like that. Now, your number line shows basically the type of measures numbers are. They are interval because your intervals are essentially worth the same. So the distance between 1 and 2 is the same as the distance between 2 and 3. They are also ratio because 0 to 2 and 0 to 4, 0 to 4 is twice that of 0 to 2. So you've got this element of ratio built in to your number line. but it is also vector. And the reason why it is vector is maybe it's a year or two afterwards, sitting in your primary school classroom, you go up to the next year, and then you see this. You see -1, -2, -3, -4, -5. You see the negative part of the number line. And at first you're a bit freaked out, but then you get explained this idea of positives and negatives, and you get it and you understand. You go, yes, this makes perfect sense. But you don't get the full story. You don't get what this means. You don't get the exciting part of this. This means numbers themselves are vectors, because what we have now done is define both a magnitude and a direction. Because let's take the number 5 and let's take the number -5. 5 and -5 both have the size of 5. They are both 5 away from 0. However, they are simply 5 away from 0 in opposite directions. So what we have then is a vector quantity. We have numbers can go right, numbers can go left. Now, this is where things get really interesting. Why can numbers only go right and left? In fact, it's incredibly illogical to say, oh yeah, we've got these vectors, but they can only move like this. They can only shuffle like crabs. It doesn't make any form of sense. It is more illogical to say that numbers can only travel right or left, or can only be right or left, or can only perfectly go along a horizontal axis. It is more illogical to say that than to say the alternative. And the alternative is, if numbers can go right and left, numbers should also be able to go up and down. And what this does is introduces the concept of a real axis and what we refer to as an imaginary axis. So numbers that exist with components on both the real number line but also have components involving the imaginary number line, we refer to as complex numbers that are typeset as the letter C. Now we tend to represent complex numbers on something called an Argand diagram. Now this is not to be confused with a normal Cartesian system. The two systems do not go hand in hand. Now an Argand diagram is named after an 18th century bookstore operator from Paris, who created this system of visualizing complex numbers. Now, complex numbers we tend to represent by the letter Z, and we say, so for example, Z1 could be a number, Z2 could be a number, just like we tend to use sort of X and Y's and things within regular number systems. We say Z is equal to X plus YI, where X is the real part and Y is the imaginary part. The I afterwards just shows that it is imaginary. So for example, the number 5 would just be 5 and plus 0i, it would just drop away, like generalized algebra. If I wanted to have a complex number that was, say, 3 along on the real axis, 4 up on the imaginary axis, then I could write that as, so this could be Z1, I could say that Z1 is 3 plus 4i. So essentially I can represent these numbers on this type of system. Okay. Why? What all I've brought up so far is it makes logical sense for there to be this imaginary axis. However, we haven't really justified why this imaginary axis needs to be a thing. We've said it could be, and it makes sense for it to be. But what is it in the world of maths that makes this happen? And it's at this point I leave you on the cliffhanger. Feel free to go and adventure into the world of maths and see what you can find about complex numbers. It is a really, really exciting area of mathematics. At Further Maths, we really just brush the surface incredibly lightly with this, but it is such a brilliant way and it completely reinvents how you think about mathematics. We do a lot of stuff that aren't complex related in Further Maths as well, but are really, really cool. We do things like vectors across 3 dimensions. We do volumes of revolution, so essentially rotating a graph around an axis to create a 3-dimensional shape. We do things like harmonic motion, which is so good for modelling purposes. There's a lot of incredibly exciting stuff within the Further Maths qualification. If you've got any questions about that, please get in touch with me. I'm happy to answer any questions. If you want to talk to me about anything that's in this video or anything else with regards maths and Further Maths over the summer, I am happy to answer any questions that you may have. As I mentioned at the start, I want to give you a bit of an overview of what students who've studied Further Maths and Maths at New College Durham have went on to do. A lot more variation than you may think. Obviously, there is maths degrees, physics degrees, pure maths degrees, aeronautical engineering, computer science, but also things like education studies, animation, biomedical sciences has cropped up a couple of times as well, and also liberal arts at Durham. A lot of Russell Group universities in there, so Edinburgh, Southampton, Newcastle, and a lot of that is down to the challenge that Further Maths entails. It shows that you can study to an incredibly high standard. It is a very rewarding qualification, and it's a qualification that a lot of institutions look on incredibly highly. So again, any questions that you'll have about maths, Further Maths, whether it's equipment, whether it's content, whether it's things like calculators, or just any questions about anything that you can be doing over the summer, please feel free to email me. I'm happy to hear from you. Love talking about maths. So just get in touch and I'll answer any questions that you may have.